Welcome to this explainer. Right now, at this exact moment, there are high-stakes, microscopic battles raging inside your body. Literally every single second, a highly coordinated defense force is fighting off invisible invaders just to keep you alive. But what happens when those defenders get confused? What happens when they overreact, or worse, turn their weapons entirely on you? Today, we're going to explore the absolutely fascinating and sometimes terrifying world of immunology and immunopathology.
To truly understand these battles, let's start with a real clinical mystery straight from our source material. Picture this. A 2-year-old boy follows his mother to a grain market for the very first time. He's completely fine, no issues at all. But when he accompanies her again 2 weeks later, the moment he gets home, he suddenly develops severe difficulty breathing. Why in the world did this terrifying reaction only happen on the second visit? Keep that in the back of your mind, because we are going to solve that exact mystery together.
So, here's our roadmap for today. We're going to start by meeting your baseline immune system, examine its antibody arsenal, and then dive into hypersensitivity, autoimmunity, and finally immunodeficiency.
Let's jump right into Section 1, Meet Your Immune System, the baseline heroes.
Think of your immune system as having two main branches, the innate and the adaptive. The innate system acts as your non-specific first responders. It's your skin, your mucous membranes, and cells that just generally attack anything that looks foreign. But if an invader manages to break through those initial lines of defense, well, you need the heavy hitters. That is your adaptive immunity, your highly specific, specialized third line of defense. The crucial trade-off between these two systems really comes down to speed versus memory. The innate system is incredibly fast, we're talking minutes to hours, but it has very low specificity and absolutely no memory. It basically treats every threat the same way, every single time. The adaptive system, on the other hand, is a bit of a slow burn. It can take days or even weeks to mount a response, but its specificity is off the charts, and most importantly, it remembers. Once your adaptive system defeats a pathogen, it retains a lasting memory of it, ready to strike back instantly if that exact same invader ever dares to return.
Now, this adaptive memory is driven by the special ops of your immune system, B cells and T cells. B cells, which mature right in your bone marrow, synthesize and secrete targeted antibodies that bind to specific pathogens. T cells, which mature in the thymus, are a bit more hands-on. You've got cytotoxic T cells acting as literal assassins, physically puncturing virus-infected cells. And you have helper T cells, which act as command centers, secreting cytokines to direct the rest of the immune forces.
So, now that we know who the soldiers are, let's look at their gear. Section 2, the antibody arsenal. When we break down the 5 immunoglobulin or antibody classes, it's pretty revealing. Notice that IgG makes up a massive 75% of the arsenal, handling the bulk of your antiviral and antibacterial defense. Then you have IgA protecting your secretions, IgM acting as those critical early responders, and IgD helping B cells mature. But pay special attention to IgE. It makes up just 0.004% of your total antibodies. It's a tiny, tiny fraction. But this specific weapon is the absolute trigger for massive allergic and hypersensitivity reactions. Keep IgE in mind, because it's about to become the star of our story.
And that brings us to the main plot twist. Section 3, Hypersensitivity. What exactly happens when our hypercompetent protectors go rogue and completely overreact to something harmless?
There's a brilliant little mnemonic from our source material to map out the 4 types of hypersensitivity when things go wrong. SCID. A is for anaphylactic, or type 1. C is for cytotoxic, or type 2. I is for immune complex-mediated, type 3. And D is for delayed, type 4. For today's explainer, we're going to focus heavily on the first two, the rapid, explosive type 1 reactions and the cell-destroying type 2 reactions.
Let's dive into type 1, because this actually solves the mystery of our 2-year-old boy at the grain market. Remember how he was completely fine on his first visit? Well, that was the sensitization stage. He inhaled an allergen from the market, maybe some pollen or grain dust. His immune system saw it, flagged it as a threat, and his B cells produced those super rare IgE antibodies we just talked about. But here's the trick. Those IgE antibodies didn't launch an attack. Instead, they silently attached themselves to the surface of his mast cells, effectively arming them like biological landmines waiting for a trigger. He felt absolutely nothing.
Then, fast forward 2 weeks, the boy goes back to the market. This is the re-exposure. The exact same allergen enters his airway, but this time, the landmines are set. The allergen binds to those primed IgE antibodies, cross-linking them together. This sends an immediate frantic signal to the mast cell to essentially burst open. It's a process called degranulation. The cell violently releases a massive flood of preformed inflammatory chemicals, mostly histamine, directly into his system.
And what does that microscopic explosion of histamine actually look like for the patient? It causes a terrifying physical cascade. Here's exactly how that allergic degranulation manifests as an asthma attack. The trigger factor causes massive, rapid airway inflammation. That inflammation forces the airways to hypersecrete thick mucus, while the smooth muscles around the airways violently contract. This creates a severe narrowing of the breathing passages, which finally manifests as that awful wheezing, coughing, and chest tightness the boy experienced as soon as he got home. When comparing a normal, wide-open airway that allows air to flow freely to an asthmatic one, the difference is staggering. You have this massive muscle contraction and swollen bronchial membranes severely narrowing the passage. It's a literal structural bottleneck, caused entirely by an immune system that convinced itself a tiny speck of dust was a mortal threat.
So that's type 1, the immediate overreaction. Let's pivot to another clinical scenario to look at the C in our acid mnemonic, cytotoxic hypersensitivity. Imagine a 45-year-old patient with blood group A receives a blood transfusion during surgery. Within just 30 minutes, he develops a fever, chills, dark urine, and his blood pressure absolutely plummets. This is a total medical emergency. What went wrong here?
What's happening in this scenario is a type 2 or cytotoxic hypersensitivity reaction. The patient most likely received the wrong blood type. His own antibodies recognized those transfused red blood cells as foreign invaders and aggressively locked onto the antigens right on those cell membranes. Once attached, those antibodies activated the complement system. This is a series of proteins that literally punch holes in the target cell, causing it to lyse or burst apart. His own immune system is rapidly destroying the newly transfused blood cells, triggering that life-threatening physical reaction.
In that blood transfusion, the body was attacking something foreign. But what happens when the body decides its own tissues are the enemy? Let's look at Section 4, Autoimmunity, the ultimate betrayal.
To really grasp autoimmunity, you first have to understand immunologic tolerance. Look, your immune system is incredibly lethal. To prevent it from killing you, your body has fail-safes built in, central and peripheral tolerance mechanisms. Basically, during immunocell training, any cell that shows a tendency to attack your own self-antigens is either deleted, suppressed, or forced into an unreactive state. Autoimmunity is, quite simply, the catastrophic breakdown of this do-not-attack mechanism. The tolerance fails completely, and the weapons are turned inward.
When this tolerance breaks down, the collateral damage usually takes two forms. It can be organ-specific, launching a highly targeted strike against a single system. For instance, in type 1 diabetes, the immune system specifically assassinates the insulin-producing cells right in the pancreas. Alternatively, it can be non-organ specific. This is a systemic, full-scale war against multiple body tissues all at once, which is what we see in devastating diseases like lupus or rheumatoid arthritis.
All right, final section. We've seen what happens when the immune system overreacts or attacks itself. But for Section 5, we have to look at the exact opposite problem, immunodeficiency. What happens when the shields simply fail?
Immunodeficiencies broadly fall into two categories. You have congenital deficiencies, meaning you are born with missing or defective defense components. This could be a lack of B cells, T cells, or stem cell defects like severe combined immunodeficiency. Then you have acquired deficiencies. Here, you're born with a perfectly healthy immune system, but you lose your defenders over time due to external factors. This could be triggered by severe malnutrition, advancing age, or viral infections like HIV, which specifically hunts and destroys those T helper command cells we talked about earlier.
And that brings us to the end of our explainer. From the rapid, innate first responders to the highly specialized adaptive special ops. From the silent sensitization of a sudden allergy to the breakdown of autoimmune tolerance, your immune system is making critical life-or-death decisions for you every single millisecond. The question is, with a microscopic defense force working this tirelessly to protect you, are you doing everything you can to take care of your greatest defenders? Thank you so much for exploring this with me. Keep learning and keep asking questions.